All right, this is the second half of this topic that we're jumping into about what derivatives tell us. So this is what derivatives tell us, part two. And really, you can think of this as what the second derivative tells us about. We talked about the first derivative and how we can use the first derivative to hopefully find where a function is increasing or decreasing. We defined this idea of a critical point, and then we built the first derivative test to help us find local maxes and local mins. And we know that we can use those critical points to do a whole bunch of stuff. Maybe I'm mixing up when we talked about what. I don't remember. But anyways, when we're talking about derivatives, the second derivative is going to tell us about something called concavity, and then we're going to define this idea of an inflection point. We'll use the second derivative to find the intervals where a function is concave up or concave down and define those inflection points specifically. And then we'll use the second derivative test to find some more local extrema. The second derivative test is going to be a derivative test using the second derivative. Wow, imagine that. So let's get this rolling. So if we start this off with an idea of concavity, I've got these two pictures, and I want us to just focus on comparing and contrasting these things. How are they the same? How are they different? Or maybe we'll say how are they similar and how are they different? In terms of some similarities, maybe I'll just start writing this up here. Both graphs, oh my gosh, there we go, are increasing on the interval from 0 to 1. They both start at the same point, 0, 0, and I don't want to say end. Yeah, I'll just say they end at 1, 1. Let's pretend that they stopped there. I drew them going further, but whatever. We're just looking at this little interval. But the thing that's different is the curvature is different, right? And so that's what we're focusing on when we think about concavity. What I want to do is start drawing some tangent lines, and we'll be able to get a pretty good idea of how the curvature is changing by just looking at some tangent lines along the way. So I'll probably just draw 3 tangent lines. I'll do my best to actually make them tangent. It's kind of difficult sometimes, though. There and there. And so what I want to do is compare the slopes of the tangent lines. As x moves from 0 to 1. So as we move from left to right, what happens to the slopes of these tangent lines? Here on this first one, we can say the tangent lines get steeper. So if the slopes are positive already, both graphs are increasing, we can look at all these tangent lines, and it looks like they've got a positive slope. The slopes are getting more positive. Or if you wanted, you could say the slopes are increasing. So what we're going to say is that f prime, maybe I'll say the first derivative, is increasing. And so that's something that we can talk about. Over on this one, we can see that the slopes, or the tangent lines first, are getting less steep. They start off really steep, and then they start leveling out a little bit. The slopes are getting less positive. You could say that first slope right around here is really, really big. It's like maybe 10, I don't know. And then this slope is like 2, and then this slope is like 1. So they're still positive, but they're getting less positive. So that means the slopes are decreasing. And so we could say the first derivative is decreasing. So what this really means in terms of second derivatives is if the first derivative is decreasing, then we're saying the derivative of the derivative is negative. And over here, we can say if the first derivative is decreasing, I wrote negative and I wanted this to be positive. If the first derivative is increasing, we can say the derivative of the derivative is positive. Here, the first derivative is decreasing, so the derivative of the derivative is negative. So if we wanted to talk about this in terms of second derivatives, here we can say the second derivative is greater than 0, and here we can say the second derivative is less than 0 on this interval. We'll call this one concave up, and we'll call this one concave down. Notice that this has nothing to do with the direction that the graph is moving. On both of these pictures, our functions are increasing. On both of them, all of the tangent lines that we've drawn have a positive slope. But on this first one on the left, the slopes are starting as small positive values, close to 0, and then they're getting steeper and bigger. And on the second one, our slopes are starting as very big positive values, and then they're getting closer to 0, less and less steep. So this is the idea of concavity or curvature. Our second derivative is going to help us out with this. So here's our definition of concavity. As long as f is differentiable on an open interval I, then if f prime is increasing, then f is concave up. And if f prime is decreasing, then f is concave down. Notice this is the thing that we'll really use mostly, is if the second derivative is positive, that means that f is increasing, or f prime, sorry, is increasing, and that means that f is concave up. And if the second derivative is negative, that means f prime is decreasing, and that means f is concave down. I'll use CU and CD to represent those pretty well. I want to draw some more pictures, but I also want to talk about this idea of an inflection point. If f is continuous at some point C, and it changes concavity at C, it goes from concave up to concave down, or from concave down to concave up, then f has an inflection point at C. Another way of thinking about this is that f prime changes from increasing to decreasing, or decreasing to increasing. Or another way of thinking about this is that f double prime changes sign, meaning our second derivative goes from positive to negative, or from negative to positive here. That's important, and that sounds familiar. We had these critical points earlier. Those were the spots where the first derivative was either equal to 0 or didn't exist, and we said those were important because those were the only possible spots where the first derivative could change sign. And then our first derivative test came in and said, hey, look, if the first derivative goes from positive to negative, that means that f goes from increasing to decreasing, and there was a max here. And we could talk about what that looks like. Here, we're saying if our second derivative goes from positive to negative, then that means f goes from increasing to decreasing, which means, f prime, our first derivative, goes from increasing to decreasing, which means f goes from concave up to concave down. We'll call this point in the middle an inflection point. So it's not a local maximum or a local minimum, it's an inflection point. I want to draw some pictures of inflection points just so we can see what they look like. And I also want to draw in some, how do I do this? There we go. I want to draw in some more intervals of concavity just so we can get a feel for what that actually does look like. So I'm going to draw a couple of intervals. We had something that looked like this, and we had something that looked like that. And this was when f prime was positive. I want to look at what happens when f prime is negative. We have a decreasing thing, something like that, or something like that. Notice on this first one, our slopes are starting very negative and getting less negative. So our slopes are increasing, actually, because they're starting really, really, really negative at like negative 10, and then they're getting closer to 0. They're moving up. That's the same as if we have a positive slope that gets steeper. So this is still concave up. And over here, we can draw these tangent lines, and we can say this negative slope is getting more negative, just like this really steep positive slope is getting less positive. Our slopes are decreasing here. So this is concave down. I think the easiest, or maybe I don't want to say easiest, maybe the most basic version of this. I'm going to move this, by the way, right there, just to save myself some space. The most basic version of uncovering concavity on a graph is to just draw tangent lines on here and just follow the slopes and see what's happening to specifically the slope of these lines. This is a small positive slope getting bigger, so it's increasing the slope, so that means it's concave up. But another thing that you'll also notice is that for these two pictures that are concave up, notice the function is sitting on top of the tangent lines. So that's a really important way or maybe helpful way of identifying intervals of concavity on a function. If you look at a function with some curvature and you draw some tangent lines, wherever the graph sits on top of the tangent lines, that's where it's concave up. And notice on the other two, our graph is sitting below the tangent lines. So whenever it's sitting below tangent lines, we know it's concave down. Another way of thinking about this is up like a cup, down like a frown. This is a silly little saying, a silly little rhyming thing, but if we take those two concave up sections, here and here, and put them together, doesn't this, maybe actually I'll do this in a different color. Doesn't this kind of look like a little teacup? So concave up like a cup, and this is concave down like a little frown. So up like a cup, down like a frown. That might help you visualize concavity as well. One of the other ways that I always have visualized concavity is to just think about parabolas. Oops. Let's say we've got a function that looks like this. I'm going to just try and cut this up into some sections that look like little parabolas. So I'm going to first say, well, this kind of looks like, oh man, a parabola that's opening up, but then somewhere around here it switches to a parabola that's opening down, and then it kind of switches again somewhere to a parabola opening up, and then it switches back down to a parabola going down, and then it switches here somewhere opening up, and then it switches again somewhere in there to a parabola going down. You'll notice that all of the green spots are concave up, and all of these red parabolas that I drew are concave down. And here, the cool thing is we can kind of see these points at which the concavity changes. Now, I'm just kind of guessing with these. It's hard to tell with inflection points sometimes. But these inflection points are specifically the points at which concavity changes. And so if we can get good at just visualizing that, we can still see these inflection points. They're kind of like these weird points in between local maxes and local mins. They're not always halfway in between, so don't get like married to that idea. But they are somewhere in between these normally, and it's where the concavity changes, the curvature changes. So visualizing these, I think, is sometimes a tricky thing to do, but hopefully that'll be at least a helpful start for that. So, okay, how is all this stuff different than the first derivative sign chart? We said we were looking at where the second derivative changes sign, and so we can use the intermediate value theorem and all that kind of stuff. What we'll notice is that it's not really different at all. So here's an example. Let's find the intervals of concavity and locate inflection points. Now, again, when we talk about intervals of concavity, we're really going to say where is f double prime positive, where is f double prime negative. The inflection points, where does f double prime switch signs? Well, the intermediate value theorem says that as long as the second derivative is continuous, the only way it can switch from positive to negative is if it crosses 0 or doesn't exist. So we are going to look for points where f double prime equals 0 or f double prime doesn't exist. This sounds familiar. Almost like critical points, right? Well, if we're going to do this, we obviously need the second derivative, so let's just find it. The first derivative is, what do we got here? 12x cubed minus 12x squared minus 12x plus 12. Oh, that's cute. I didn't remember that. Anyways, our second derivative then, we got all these 12s in here. We've got 36x squared minus 24x minus 12. Hopefully this factors nicely because we want to set this thing equal to 0. I might first just factor out a common factor of 12, and then I've got 3x squared minus 2x minus 1. And I want to factor this. So first off, I'll just notice, hey, look, the second derivative not existing, not going to happen. This is continuous everywhere because it's a polynomial. So f double prime exists everywhere. Normally you're looking at like where does it divide by 0 and that kind of thing. And our second derivative doesn't have any of that. Then we're going to try and factor this. We'll see, can we factor this? Numbers that multiply to get negative 3, add to get negative 2. That's going to be negative 3 and 1, right? So this is really 12 times 3x squared minus 3x plus x minus 1. And that's going to be 12 times 3x plus 1 x minus 1, something like that. Cool. You can check that on your own. But now, when we set this equal to 0, we get 2 values. When we were doing the first derivative, we would call these things critical points. These are not critical points, technically, because critical points are specifically defined as places where the first derivative is equal to 0 or doesn't exist and is inside the domain of the function. These we'll just call like interesting points that we're going to look at. There's not a well-defined name for these. I've heard people call them possible inflection points. I've heard people name them after themselves. We won't really call them anything. We'll just say, hey, these are some special, interesting points that we are going to care about here that might actually help us find inflection points. Because remember, these are the only possible spots where our second derivative can change sign. So we're going to set up a sign chart between these values. So let's go ahead and do that. I'm going to try and remember what our second derivative is, but I'll probably forget it. Maybe I can copy it. Let's see if that works. I always forget if I can do that kind of thing. Oh well. Let me just go back and remember it. 12 times 3x plus 1 times x minus 1. So here's our second derivative. 12 times 3x plus 1 times x minus 1. And we were going to set up a sign chart. And our x values were negative a third and 1. And remember, we're looking at the intervals in between. So we're going to look at all the values less than negative a third. We'll see what happens when we put those into the second derivative. Well, if we put in really negative numbers, stuff less than negative a third, then this term here, I shouldn't say term, this factor here is negative, and so is this one. And so we get a negative times a negative. That makes this positive. You'll notice that if you put in something like 0 in between negative a third and 1 here, this is 12 times 1 times negative 1. That's going to be negative right here. And if you put in something a lot bigger than 1, you're going to get a positive number here, a positive number here, positives all across the board. Remember, we're really looking at these intervals from negative infinity up to negative a third, from negative a third up to 1, and from 1 up to infinity. And our sign chart now, we have to interpret what this means for f. Now, this doesn't mean increasing, decreasing, local max, or anything like that, because these are signs of the second derivative. So what this means is that our function is concave up. F prime is increasing here. That means f is concave up on this interval. And now if our second derivative is negative, that means f prime is decreasing, and so we'll say f is concave down. And on this interval, we have concave up again. And so we've got these inflection points happening. At x equals negative third and x equals 1. These are the spots where we're changing concavity. We're concave up on the interval from negative infinity up to negative a third, and from 1 up to infinity. And we're concave down on this interval in the middle. You could think about what this fourth degree polynomial looks like. A fourth degree polynomial, normally, I don't want to put in axes because we don't know exactly where it is, but a fourth degree polynomial might look something like this, right? And so we're expecting to find 3 local maxes and local mins, but the inflection points that we're finding are right here. So we've got 2 inflection points at -1/3 and at +1, and it's going from concave up to concave down to concave up in between those things. So that's what this example looks like. Not too bad. What you'll notice is that for other functions, this might get a little bit more hairy, right? This isn't a polynomial function anymore, so finding the derivatives might get a little annoying. So let's see. Well, actually, you know what? Before I get too far into it, I'll write out the derivative here. Oh boy, that's ugly. There we go. Remember, that's our derivative of inverse sine. But anyways, you go ahead and find the second derivative. You're going to have to use the chain rule. I'll give you a hint. Write it this way. 1 minus x squared to the -1/2. That might be helpful. Find your second derivative. See if you can find those values where the second derivative is equal to 0 or doesn't exist, those values that are guaranteed to exist by the intermediate value theorem. And then we can go ahead and find our sign chart, set up all those intervals, and check the signs of the second derivative on those intervals. That'll tell us where f is concave up or concave down, and then help us find inflection points. So pause the video and give that a shot. Actually pause it. For real. Like, grab a pencil and paper and see if you can work this problem out. I'll just wait here all day. All right, here we go. Let me just show you this now. Okay, so you might start getting into this a little bit, and we're going to show you that there's something that we kind of haven't talked about that we'll notice. But anyways, let me just catch you up. Hopefully you did the chain rule, and so you bring this exponent out front, subtract 1, but then multiply by the derivative of the inside part. Notice the -2 and the -1/2 cancel each other out, and so we get an x in the numerator. I took that negative exponent, popped it down in the denominator. So this is the second derivative, the way that I'll write it. Now remember, we talked earlier about how it's really important to try and get comfortable with rewriting these things, because now it's really easy for me to see that any of those x values I find by setting the denominator equal to 0, those are ones where the second derivative doesn't exist. And any of the things that I find where the numerator is equal to 0, well, those are the ones where the second derivative is equal to 0. So we went ahead and solved those, and I found 3 values, 0, and then plus or minus 1. And then we can get a little bit kind of into it and just set up our sign chart and go from there. But we're missing one thing. There's one thing that we might not notice. Maybe we'll notice when we start finding some signs. Maybe if we start way over here or over here, and we try and pick really, really, really big x values and put them in here, we get 1 minus something large, and that's negative. That might be a problem for us. Because notice what the exponent is. It's 3/2. That means there's a square root there. And so we have some problems because their second derivative doesn't exist on these intervals. Remember, the domain of the sine inverse function is, -1 to 1. And that means the domain of f double prime is open from -1 to 1. I already know it doesn't exist at positive or -1 because I set those things equal to 0. But that means we don't actually look at these intervals. Notice when you do that, you're going to get these negatives under square roots. Our sine inverse function doesn't actually exist there anyways. And so these are the ones that we have to look at. So just be a little bit careful when you're thinking about functions. Try and keep the domain of the function you're looking at in mind. Anyways, now we can go ahead and start finding some signs of the second derivative. You can say, well, what happens if I put in a small positive number for x? When you square it, it's going to be positive, but it's small, right? So 1 minus that, that's positive. And so you have a positive on the bottom. Now notice the denominator is going to be positive no matter what. We'll talk about that later. So I have a positive number on the top, positive number on the bottom. Positive divided by positive is positive. In this interval, I'm putting in something between -1 and 0. So actually, maybe I'll write this as a fraction. Positive over a positive. So that's positive. All right, so on this one, we're going to put in a negative number. If you put that in for x up in the numerator, we get negative over 1 minus that thing squared. When you square it, it becomes positive, but remember it's small. It's like negative half or something like that. So when you square it, it gets even smaller. So 1 minus that is still positive. And then you raise it to that exponent, and it's still positive. So this is a negative over a positive, negative, meaning your function goes from concave down to concave up. And there's an inflection point in between right here at x equals 0. So our inflection point is when x equals 0. If you wanted to find the actual point, it ends up being 0, 0 in this case because your f of 0, your y value, is just sine inverse of 0, which is 0. Cool. Our intervals from -1 to 0, it's concave down. Oops. And from 0 to 1, it's concave up. Neat. If you remember the graph of the sine inverse function, it ends up looking a little bit like this. It's concave up and concave down. We end up, oh no, this is my straight line ruler. It's going to be concave down here, so it ends up looking something like that, and then like that. And that's not a perfect picture of it. You can think of the reflected sine curve if you want, but that's an okay picture of our sine inverse function. Concave down from -1 to 0, concave up from 0 up to 1. There's that inflection point in the middle where it switches sign of the concavity. All right, so let's talk about the second derivative test for local extrema. What the heck is this thing? So the first derivative test for local extrema is that first derivative sign chart. And so a lot of people want to say that this sign chart, that's the second derivative test. It's the same thing as the first derivative test, but you're using the second derivative and talking about concavity. Now, because math and calculus is very clear, that's not the case. So we mix up the naming of stuff, which is a little bit confusing. The second derivative test, we'll try and keep in mind, this is the second derivative test for local extrema, local maxes and local mins. That sign chart that we did found inflection points. So what we're really trying to get at is how can we use concavity to tell if a point is a local maximum or a local minimum? And it's not too bad if you just draw it out. So we're going to suppose the second derivative is continuous on an open interval around some point, meaning we're going to be able to evaluate the second derivative nicely. And the first derivative is equal to 0. So this is kind of like a critical point, but it's a very specific type of critical point. It's specifically one with a horizontal a horizontal tangent line. So specifically, this is the type of critical point that it is. And we want to check the second derivative. So let's just draw it. Let's take that first line on there. And if you're filling this out on that handout that you've got, you should see something really similar to this on your handout to fill out. So if the second derivative is positive, that means your function is concave up. So that's up like a cup, or you can say like an upwards facing parabola. And since it has to brush up against this tangent line that's horizontal, you'll notice, hopefully pretty easily, that there's a local minimum at x equals c. Then, similarly, if we go ahead and draw another line, I'll just do it over here, and we draw another critical point, but on this one, oops, I keep forgetting to turn off my ruler. There we go. So on this one, we had concave up with a local min. On this one, we're going to say, well, what happens when the second derivative is negative? It's less than 0. That means we're going to have this downwards concavity, down like a frown, right? So there's a local max at that point. So, concave up, horizontal tangent line, local minimum. Concave down with a horizontal tangent line, local maximum. Try and keep that in mind, but really try and visualize it. I think memorizing this like positive first derivative first derivative 0 and positive second derivative, that means that we've got a local minimum. I think that's sometimes hard to just put those words together in your mind. But if you can try and get a visual of what concavity really means and what's happening with this, that might really, really help. So our last option is what's happening when you've got this horizontal tangent line and your concavity is 0. And there's a really weird thing that goes on here. A lot of people want to say, well, there's an inflection point. So it's not a local maximum or a local minimum. But the problem is that might not actually be true, because this is another possibility. You might have a function that actually has a local minimum, but it's so flat at that critical point that the concavity doesn't really register. And so it might actually be that this is a local minimum. A really easy example of this, if you want to try it, is x to the 4th. Go ahead, find the first derivative. It's 4x cubed. The first derivative is equal to 0 at 0. The second derivative is 12x squared. And the second derivative is also 0 here. But clearly, x to the 4 has a local minimum here. So it could be that there's an inflection point. It could be that there's a local minimum. It could be that this is upside down and there's a local maximum here. What we'll say is the second derivative test fails to give us any information. So this is kind of crazy, because what this means is that we have a test where one of the possibilities is just straight up, I don't know. This doesn't help. We really have no idea about what's going on, and so try something else. And so maybe instead we might get some information to say, okay, go back and just do a first derivative sign chart. Do that first derivative test and see what's happening there. Check the sign of the first derivative around that critical point. See if it changes from positive to negative, where your function goes from increasing to decreasing. We don't know. So why is the second derivative test even used? Why is it useful? We'll find plenty of situations where the second derivative test is really, really helpful and really easy to use. I'll try and show you a bunch of situations where we can use it. But more importantly, it's going to be really easily extended. So when you get to like Calc 3 and you're talking about things in multiple variables, the second derivative test is really not the hard thing to extend into multiple variables. So let me just give you some practice on something like this. Let's take a look at the second derivative test here on this specific example. And then maybe we'll do one more and we'll kind of call it there. So what I want you to do is to pause the video, find your critical points for this function. Find the first derivative, set it equal to 0, see if it doesn't exist. Grab those critical points, and then find the second derivative and plug those values into the second derivative. I'll help you with the interpretation. So pause the video and go ahead and do that. All right, so hopefully this is what you've done. You went ahead and found the first derivative. Hopefully you did some factoring, and we can get this x plus 1 times x plus 1, or x plus 1 squared. So x equals -1 is a critical point. And if you find the second derivative, you get 6x plus 6. And you'll notice that if you put -1 into this, you get -6 plus 6, which is 0. So what we'll say is that the second derivative test fails here. So this is an example where it doesn't really work out that well. What we could do then is use the first derivative test. So we'll do our little sign chart. We'll say, okay, let's take a look at this value of -1, and let's see if the first derivative changes sign here. And you'll very easily see that it doesn't, right? If you put in an x value that's smaller than -1, you're going to get some really negative stuff in here. But when you square it, it becomes positive anyways. And then when you put in something a little bit bigger than that, you square it and it becomes positive again. And so what that means is that your function goes from increasing to increasing. So there's no max or mins on here, which is kind of a weird thing. There is going to be an inflection point there, though. Notice, just because, if you set up a sign chart for the second derivative, around -1, the second derivative does change sign. You go from negative to positive, meaning your function goes from concave down to concave up. So there's an inflection point here. Now, that's not useful for us because specifically we were asked about local extrema, but here we could say there happens to not be any. Now, not because the second derivative was 0. The second derivative being 0 here just tells us we don't know what's happening. So this is maybe a weird example to look at first because we didn't actually get to use the second derivative. So go ahead and do this one. Let's find the derivatives, and then I'll let you kind of use it and see what's happening. Our first derivative, we'll have to do the chain rule on here. So this is going to be 2 times sine of x times the derivative of sine of x, which is cosine of x. Now you might notice that this is a trig identity. You might recognize this as just sine of 2x. It's like the double angle identity for the sine function. If you didn't recognize that, no big deal. I'm just telling you this. It'll make it easier to find the second derivative. Because now we can do a little chain rule. The derivative of the outside, we've got a cosine of 2x multiplied by the derivative of the inside. So we'll just call this thing 2 cosine 2x. Okay, so if we want to use the second derivative test, we first need to find critical numbers. There's a whole bunch of them. So here, we're going to try and figure out where is sine of 2x equal to 0. If you want, you can call this sine theta equals 0, where theta is 2x. And this is when theta is, maybe I'll draw my unit circle so you can see what I'm talking about. There and there. So this is when theta is 0, pi, maybe I'll actually start off here. 0, pi, 2 pi, 3 pi, oops, etc. But then also all the negative versions. So that means that 2x is that. So x is all these things divided by 2. So x is negative 3 pi over 2, negative 2 pi over 2. I'll just call that negative pi. Negative pi over 2, 0, pi over 2, pi, 3 pi over 2, etc., etc. And now the nice thing about this is that if we try and evaluate the second derivative here, for all of these x values, it shouldn't be too bad. We're going to multiply things by 2 again. So we can think, okay, really just think about those values that we had. And then we're going to look at the cosine, and all we care about is the sign, positive or negative here. So multiplying by 2 doesn't really matter. So what I'm talking about is I'm going to look at a unit circle. I'm going to plot these angles again. They're going to be here and here, right? So they're going to be right here and here when you multiply them all by 2. And so all the ones on this side have a positive cosine, and all the ones over here have a negative cosine. Meaning, our second derivative test says g double prime is positive for 0, pi, which was really pi over 2, because remember when we multiplied it by 2, it turns into pi. Or sorry, that's not pi. I wanted pi, because then when you multiply it by 2, it turns into 2 pi. There we go, sorry. 2 pi, because when you multiply it by 2, it turns into 4 pi. 3 pi, because when you multiply it by 2, it turns into 6 pi, etc., etc., etc. And g prime is negative for pi over 2, because when you multiply it, it turns into pi. 3 pi over 2, because that's here as well. And when you multiply it, it turns into pi, or sorry, 3 pi. And 5 pi over 2. And all the negative values going up to there. And so what that means is that all of these ones, the second derivative is positive, concave up, these are all local mins. And these ones are local maxes. So we had an infinite number of critical points, and we didn't have to set up a sign chart to figure out what was going on. We can just think about the second derivative and see what's happening there. So that's kind of a nice way of doing it. Now, recognizing that trig identity along the way was really helpful for us. I can go over more examples of this kind of thing in the office hour or online or something like that if you want. So mess around with some of these. There's a good chunk of problems in the homework that I specifically ask you to use the second derivative test on just to get you used to trying it. So see how that goes and let me know if you have any questions.